Hi everyone, I am Mohammed Sarmad Mir, working as an early stage researcher for LIoT projects in IMDEA Networks, Spain. Today I'm going to present you work on non-linearity of LEDs for VLC IoT applications. Internet of Things are actually the interconnected devices that transfer information over a wireless link. It is believed that by 2025, more than 75 billion IoT devices will be installed worldwide. With the increase in demand of devices, there is increase in the requirements in terms of high data traffic to develop simple modulation techniques that require very less energy and more reliable devices. So we are working on visible light communication as an enabling technology for IoT devices to transfer information over a wireless link. So normally, traditionally, VLC signal is modulated within the linear region of LED. So in this work, we explore that is this the most appropriate region for IoT applications. Here you can see that in figure 1, the forward voltage is shown on x-axis and normalized output luminous flux on y-axis. The graph shows the transfer function of the LED, and the green line shows the linear region of operation, and the blue line shows the full region of the approach to full region of operation. And this red dot shows that in both the approaches, the output luminous flux is same for fair comparison. On the hardware side, we use the DC-DC converter that converts the 5 volts to 12 volts, and then there are two resistors. Basically, it is a open VLC platform that we use, but we modified it by adding a second path to the LED. And these resistors R1 and R2 are used to set the high and low levels of the amplitude modulated signal as per the approach 1 or approach 2. On the theoretical side, we see that the power of LED is directly proportional to the current swing, to the square of the current swing. The length of these arrows shows the current swing. We have a higher current swing in full region approach. But on the other side, for SNR, the SNR is proportional to the fourth power of current swing. So it may be worthy to work on full region rather than on linear region, because we see that we will get the increased SNR, but at the cost of increased power. So these are some LED effects that we observed. The first one is the capacitance effect. We can see on x-axis it is time, and on y-axis it is received signal amplitude. And at higher frequency, we see that we don't see the sharp sharp square signal, but it is more like a sinusoidal signal, because the LED is not quick to respond to the modulation rate, which shows the capacitance effect. In figure B, we observed that while we operate the LED at a low frequencies, for example, this blue dotted line, you can see at low frequency it shows that at the high values the signal is distorted, which is basically due to the temperature issue. In the third graph, you can see modulation rate on x-axis and illuminance on the y-axis. In the start, you can see that with the full region approach, due to the temperature issue, we get less illumination, and the capacitance effect is prominent at the higher modulation rates. So a VLC link designer must be careful with these issues. This is the experimental setup. We use the modified Open VLC platform both as transmitter and receiver. Here you can see we use the lux meter to measure the illumination. And this is the LED photodiode and two resistors to set different levels of modulated signal. So these are some results. The first one is from the communication link performance, and you can see that on x-axis it's a transmitter receiver distance. On the y-axis it's a received electrical power in dBm. The full region and the frequency sweep from 1 kilohertz to 1 megahertz, and the solid line shows the full region approach, and the dotted line shows the linear region approach. And we can see that the gain in the received power electric, we received the gain of around 15 dB using the full region approach. Hence, we can achieve the higher modulation rate, and the higher range of communication can be achieved. And as expected, larger the distance, lower the received electrical power. And also in the second graph, you can see that we have a transmitter receiver distance on x-axis and SNR on the y-axis. The full region approach, with the full region approach, we see that we get at least improvement in SNR of 2 dB when we are working in a full region approach. Also, we see that the SNR decreases as the modulation rate increases. Ideally, there should be like a 10 dB increase for every 10x increase in modulation rate, which is prominent here between, for example, green and red lines. You can see it's at a 10 dB distance difference. So these results are aligned with the theoretical concept I showed just before. And here you can see that we get the increase in SNR, but at the expense of 10% more power consumed in a approach two, in the full region approach, as compared to the linear region approach. So that's the price you have to pay to get the better range and higher modulation rates. Here you can see that we use the solar cell in the applications where the solar cell is used as a receiver. We wired this is the received signal at the output of the solar cell, and we use different modulation rates from 100 hertz to 1 megahertz. We have time on the x-axis and amplitude on the y-axis. So you can see that in the figure A, due to the temperature issue with the full region approach, the average of the signal is less than the linear region approach. So we expect less harvested energy in this case. But in all other cases, for B, C, D, and E, both approaches provide the similar average. So same harvested energy we get the same harvested energy from the solar cell. Another problem is when we use the full LED approach, it may saturate the solar cell for higher values. One other positive side of using the full region approach is that when we are using the solar cell as receiver, we can see that for example, in 100 kilohertz, we see a change in the signal, and when we are operating on a full region. But if at the same frequency we operate at a linear region, we don't see any change in the signal. So it means we can demodulate the signal at higher frequencies when we are using the full region approach, which helps us to achieve the higher data rates. So as a conclusion, we can say that working in the full LED region provide better communication performance than working in a linear region approach. A gain of around 15 dB in the electrical received power, and we get the increased range for the same SNR value, with the penalty of around 10% increase in the total power consumption of the LED. And also when we are using the solar cell as receiver, the full region approach allows achieving higher data rates. Thank you very much for listening to the presentation. If you can ask question in the coming question and answer session, or you can send an email at this email address. Thank you very much.